So in the last lecture, we left off talking about the align-of operator, which essentially gives us a way to query the alignment of a particular type. In this lecture, I want to start out by talking about the align-as specifier. In some contexts, alignment can be controlled by using the align-as specifier. One context in which we can use it is when we're declaring a variable. We can specify its alignment in memory by using the align-as specifier. Another case is when we're defining a class. We can impose a stricter alignment than what would normally be done by default by the compiler by using the align-as specifier. So to give an example of using the align-as specifier when we're declaring a variable, here we have this variable x, which is an array of char, basically an array of 8,192 chars. And because char has an alignment of 1, normally there wouldn't be any particularly strict alignment requirements on this array. It could essentially start anywhere in memory. But suppose for some reason we wanted to start at an address which is an integer multiple of 4,096. Then what we can do is we can add in this align-as specifier with 4,096 as the argument. And what this says is make sure that the address at which this object starts is evenly divisible by 4,096. We can also use align-as when we're defining classes. So an example of this is here we have this class called widget. It's a very simple class. It just has a single data member. Because the data member is a char, this class will probably have very, very weak alignment, like very relaxed alignment restrictions. Probably it'll just be 1. But suppose that we want to have a stricter alignment for this type for some reason. Then we can add in an align-as specifier, and then we can give it some sort of alignment. In this case, we're giving it the same alignment as the magical type from the standard library called max_align_t, which is just a maximally aligned type. The next thing I want to talk about are new and delete expressions. So when we have objects that have dynamic storage duration, in other words, objects that once we create them, they don't go away until we explicitly get rid of them. These are what we call dynamically allocated storage. We use new expressions to create such objects or arrays of such objects. And the particular syntax for a new expression, we have an optional scope prefix, which is either a : or nothing at all, followed by new, followed by a placement argument list in parentheses. And this is optional, so you don't need to provide any placement arguments if you don't need them. Then we have the name of the type that we're creating and an initializer possibly as well. Just as a matter of terminology, in the case where we do actually provide some placement arguments, we refer to this as a placement new expression. So placement new just simply means that the expression has some placement arguments. And what's returned by the new expression is just a pointer to the object that was created in the case of a non-array type. And if we're creating an array type, then it's a pointer to the first element in the array. So on this slide at the top, I have a few examples of new expressions. So maybe looking at the first one here, this is going to create an int and then essentially return a pointer to the int that was created. There's no initializer provided here. There's also no placement arguments because there's no parenthesized list of arguments between the new and the int. Here we're creating an integer, an object of type int, and we're giving an initializer of 42. There is no, again, in this case, there is no placement arguments. There's nothing in parentheses between the new and the int. If we look at this line down here, we have an example where some placement arguments are being used. We have this parenthesized list of arguments between the new and then the name of the type that we're creating. This is where the placement arguments appear. Then if we look maybe down at the last example here, we have a case where we're using this : in front of the new. And as we'll see later, this just controls how overloading works with respect to some of the operations that are performed by a new expression. In terms of what a new expression actually does, it basically performs sort of 2 key things, and then if something goes wrong, there might be a third thing that it does, which is the item number 3 in this list below. So the first thing that it does is it invokes what's called an allocation function to obtain an address in memory where the new object or array of objects is to be placed. So that basically, if you're going to create something, the first question you need to answer is, where am I going to put it in memory? And this is what the allocation function does. Its sole purpose in life is to say, you should put this new thing that you're creating here. And basically, it gives you a pointer to where it should go in memory. Then once you have somewhere to place the object or array of objects that you're creating, then you invoke constructors to create that object or objects if it's an array in the place that the allocation function told you should create it. But things can go wrong. For example, maybe we've allocated some memory. In other words, step 1 is succeeded. Then we proceed on to step 2, and then we invoke a constructor, but then the constructor throws an exception because something goes wrong. In this case, the object that we're trying to create with new is not going to be successfully created, and we don't want to leak the memory that was allocated successfully in step 1. So in this case, this leads to step 3 here, which is that if the constructor fails, in other words, we've allocated memory, but then the actual initialization of the object fails, then we have to, if there's any objects that have already been created, we need to make sure that they're destroyed in the reverse order from how they were constructed. And in addition, we need to call it the allocation function to free the memory that was allocated in step 1. So this is essentially what a new expression does. Then we have correspondingly delete expressions. So the way that we end the lifetime of something with dynamic storage duration is by explicitly using a delete expression. And the syntax of a delete expression is what's shown here. We have a scope prefix, just like we did in the case of a new expression. Either it's a colon, or it's nothing at all, followed by delete, or delete square bracket, and then followed by a pointer, an expression which is a pointer. And the difference between delete without the square brackets and delete with the square brackets is delete without the square brackets, sometimes called single object delete, a single object delete expression. This deletes an object that was created with new that was just a single object. It was created with single object new. In other words, the thing that was created with the new expression was not an array type. And delete square bracket, what this does is this deletes an array. It's sometimes referred to as an array delete expression. And this is used to delete arrays that were created with the new expression. In other words, things that had array type. The delete expression has void type. In other words, it doesn't return anything. It's just a void. And as I mentioned, the expression that's passed in here is a pointer. It does allow null pointer. It's valid to pass in a null pointer to delete. So you can say delete null, and this is defined to do nothing. It's just a no op. So it's completely well-defined behavior to delete a null pointer. It just does nothing. On this slide, I have some examples of delete expressions. Maybe one thing I should comment on before we look at these examples is that what's indicated at the top of the slide, which is that if you create a single object with a new expression, in other words, the type that you're creating, the type of the objects that you're creating with a new expression, if the type is not an array type, so you're not creating an array, you're just creating a single object, then you have to just get rid of that object by using a single object delete expression. In other words, delete without the square brackets. On the other hand, if you create an array with a new expression, then you have to make sure that you get rid of it by using delete with the square brackets. In other words, the array delete expression. So some examples of delete expressions here were, first of all, creating an int. It's just a single int object, and then we're storing the pointer that's returned by new into this variable IP, and then we're deleting IP. So notice here we're allocating or creating a single object, a single int, and here we're using delete without the square brackets, so we're getting rid of a single object. Here on this line down below, here we're creating an array of 1024 strings, and then we're taking the pointer to the first element and assigning it to ASP. And then when we call delete here, notice that we're using delete with the square brackets. So here we're deleting an array, something that was allocated as an array with a new expression. And again, it's really important that you match up the news and the deletes. So if you create a single object with new, then you have to delete a single object with new. And if you create an array with new, then you have to delete an array. So what you want to avoid are things like what's shown at the very bottom of the slide here. So for example, in this case, and these are things you don't want to do because they're really, really bad and can have quite bad consequences in terms of bugs and things crashing and so on. In this particular case, what we've done is we've allocated a single string object using new and then saved the pointer to it, this SP. And then what we've done is we've incorrectly called array delete because the thing that we allocated was a single object, but here the thing that we're trying to destroy, we're saying it's actually an array of things, but it's not an array. So this is really bad. You don't want to do this. All kinds of weird things can happen when you start doing stuff like this. And then we have sort of the dual problem, which is here we've allocated an array. So we have an array of 1024 strings. So when we delete the pointer that's returned by new here, we should be using array delete. In other words, an array delete expression. So there should be square brackets here after the delete, but we've accidentally left them out. Again, this can lead to all kinds of very strange things happening. You always have to match up your news and deletes so that if you're creating single objects, you get rid of single objects. If you're creating arrays, then you have to get rid of arrays. In terms of what the delete expression actually does under the hood, there's sort of two cases to consider: whether we're deleting a single object, in other words, it's a single object delete expression, or whether we're deleting an array, in other words, it's an array delete expression. So I'll consider the simpler case first, which is we're considering a single object delete expression. In this case, what happens is if the object is of class type, so it's some user-defined type, first it will invoke the destructor, and then it deallocates the memory that the object is sitting in. The reason why if it's a class object, if it's a built-in type, there's no destructor, there's nothing that needs to be done to clean up, so it can just deallocate the memory without doing anything special beforehand. The second case we need to consider is the array delete expression. So what happens when we try to delete or destroy an array, get rid of an array? So what happens in this case is if the array elements are of class type, so in other words, the elements in the array are some user-defined type, and they have some kind of non-trivial destructor. So the key thing is you actually need to destroy something. Because like if it's a built-in type, for example, there's nothing to destroy, there's no destructors to call. So this step here, we don't really need to do anything. But if it's not a built-in type, it's some user-defined type, and it has a destructor that actually does something, then we have to actually invoke the destructor. So the first thing that we need to do is we need to figure out how big the array is, because when we're destroying the elements in the array, we have to invoke the destructor for each element. So the first thing we need to know is how many elements are there. Then once we know how many elements there are, then we're going to invoke the destructor for each element in the array. And they're destroyed in sort of reverse order from construction. And then after that's done, then we just deallocate the memory that the array was occupying. Now, I just want to make a few comments about like why it's really, really important to not mix up the news and deletes, like whether they're single object versus arrays. And part of understanding why this can have such bad consequences is helpful to know a little bit about how things are typically implemented underneath. So what I want to do is maybe explain this by way of a picture. So I'll go to this figure here. So suppose what I want to talk about specifically here is we're doing like array new. So like what happens with array new and array delete expressions. So if we do like an array new expression, then what happens, we give it some size when we're creating the array. And although we may actually, maybe if I back up a step here, the thing that you'll notice if we just look at this code here, there's only really two lines that are of any relevance to what I want to say at this particular moment, which is this line here on line 15 and the line 26 down below. The one thing that you'll notice here is when we create an array, and this is true in general, it's not specific to this example, we specify the size of the array when we create it. But the thing that's really important to notice is when we actually get rid of the array with this delete down below, notice that we don't specify the size of the array. This is really important because this implies that the runtime system must somehow be remembering and tracking. Like basically the compiler and library are responsible for making sure that somehow they remember what the size of the array is, so that when delete is called, they can do the right thing. Because all we're saying is where the array starts. We don't say anything about how big it is. So in terms of how typically, I mean, this is not mandated by the standard, but typically how some implementations do this is something like the following. So when you do a new expression where you're allocating an array, what happens is the compiler will actually allocate a bigger chunk of memory than what you really need. Like what you need would be, suppose that the array you're allocating is an array where each element in the array has type capital T, and suppose that the size of the array is n. So if you only needed this space for just strictly the elements you're going to store in the array, you would just need n times size of t. In other words, this amount of storage. But actually what happens in reality is, in practice, is the compiler will typically allocate a little bit more than what you ask for. The reason why is it has to somehow remember what the size of the array is later, so that when you delete it, it knows what the size is. So the trick that's often used is something like this. Again, this is not mandated by the standard, but this is kind of gives you an idea about how it might be implemented, and also makes it easier to understand why it is it can be such a big disaster to mix and match single object versus array news and deletes, like not matching your news with deletes. So basically what happens when you have your new expression and you're allocating this array of n elements, or n elements of type t, the compiler will allocate slightly more space than what you've asked for. And in particular, it's going to ask for enough space that it can stick just before the beginning of your array. It's going to store how many elements there are in the array. In addition to this, it may ask for a little bit of additional memory as well to make sure that the different types are suitably aligned, because it needs to make sure that when it places this size here, that the pointer that's going to eventually be returned back to you is the start where your array starts. It has to make sure that it's aligned properly for the type that you're trying to allocate space for. So because of this, it may be necessary to add some additional padding before this size here. So essentially what happens, again, kind of summarizing from the beginning, you asked for n times size of t bytes effectively, but what happens is it goes, no, I'm going to allocate more, and it sticks in front of the beginning of the array, the actual size of the array, and then what it does is it returns to you, the person who's invoking the new expression, a pointer to the first element in the array. So secretly behind your back, although you don't know it, the compiler's actually got some other stuff that comes just before the pointer that's returned to you. Like this is the pointer you get back when you do your new expression, but little do you know that there's actually some other important data just before the start of your array. And by the way, this is why it's a big disaster. Often if you have a bug where you start to go off the end of the array at the beginning and you overwrite data that comes just before the start of the array, this can have very bad consequences, because you could overwrite this count here, which will cause lots of bad things to happen when you go to destroy that array later, for example. Anyway, so when we then get to the point where we're going to delete the array, the way things work is that when you do array delete, assuming that you've correctly done an array delete and you've not inadvertently called a single object delete, because it's an array delete, the compiler knows that you're actually trying to get rid of an array. And because it's an array, it knows that it sneakily behind your back saved the size of the array just before the start of the array. So when you call delete, the pointer that you pass into delete is this pointer here, which was the one that was returned by new. But what the language implementation does is it backs up in memory and goes a little bit before P to look at what the size of the array was. Now it knows the size of the array, and then it can invoke the destructors for the elements in the array, because now it knows the size. So this is generally how things work. Or like, again, this is one way to implement things, but this is a very common way to do things. And if you understand how things are typically implemented like this, you can see why it's very, very important that if you do a single object new expression, that you delete that object using a single object delete expression. And if you create an array, if you create an array within an array new expression, that you delete it with an array delete expression, because if you don't, then it's not going to properly handle like the way that it determines the size of the array and so on. Anyway, so hopefully that might be a little bit helpful for understanding various different issues with respect to arrays versus single objects with new and delete. This code example I don't really want to spend too much time on, but it basically what it's doing is it's just kind of illustrating. I tried this with a few different compiler implementations, and for every one of them, the assertion that appears here on line 21 passes. And basically what it's doing is it's just creating an array of objects, array of widgets of size n. And then what it's doing here is it's checking to see in the memory that comes just before the pointer that's returned by new. P is the pointer that's returned by new. It's looking just before at index -1, so this is just before, and it's checking to see if this is equal to the size of the array. And if the compiler, if the language implementation implements things the way I'm describing, this assertion will always be true. It will never fail. But this is not a requirement, though. The language, again, does not mandate that things be done this way, but often they are. And you'll see for like a lot of implementations, this assertion will pass. So I need to say a few more things about new expressions and delete expressions. So with new expressions, we saw earlier that one of the steps in the evaluation of a new expression is that it needs to call an allocation function. It needs to do something to find out where in memory do I place the object that's being created. And how this is accomplished is through something called operator new. There's actually two operators in the language, operator new without square brackets and an operator new with square brackets. And the only difference between them, the one without the square brackets, is used when you're trying to do allocation for the single object new expression. And operator new square brackets is used in the case where you're trying to allocate for an array, in the array case. And although we call these functions allocation functions, I mean, technically speaking, they may not allocate memory. It's maybe more precise to call them, like they're a function that their purpose is to tell me where to put something in memory. But that place where it's telling me to put the object that's being created, it's not necessarily the case that it just immediately at this point in time is allocated memory. It might be memory that was allocated at some earlier point in time, and it just happens to know that memory is available and it uses it, essentially. And we'll see kind of applications of this later. And there's kind of two flavors of new like allocation functions. Ones that throw exceptions when they fail, because if you allocate memory, you may run out of memory, for example, and then the operation fails, and you need to somehow signal this back to the person that invoked you. In the case of a new expression, essentially the compiler is invoking you through a new expression. So it needs to be a way to signal back to the person that invoked operator new that it's failed. So there's sort of two possibilities. In the case that you do this by exceptions, you throw a special type of exception called bad alloc from the standard library. In the case that the mechanism is not by throwing exceptions, you just return a null pointer. In other words, for the result that you say of where to place the particular object in memory that's being created, you just give it a null pointer, and it's understood null is not valid, therefore this is indicating an error has occurred. When we're using operator new, I mean, essentially one of the things that operator new gets is the passed to it is the size of the chunk of memory that's needed, how big the memory is that needs to be allocated. In the case that we're allocating an array, in other words, we're using operator new square brackets, the one that's called when we're allocating space for arrays, the amount of memory that's requested could be larger than what's actually needed just to store the array data itself, for the reasons that we saw in that hand-drawn figure that I went through a moment ago. I mean, often the implementation will need to allocate a little bit more, because somewhere it needs to store the size of the array as well. So this can be used at the time that you're deleting the array. And again, if a new expression, we saw new expressions, they can use the colon operator. So you have something that looks like colon followed by the keyword new. And what the colon does, its presence or absence controls how the allocation function's name is looked up, because it can be overloaded. So it can be at the global scope, there's like a global operator new function, and then there's also ones that can be provided on a per class basis. And the colon operator says, if it's present, it says to use the global version of the operator, as opposed to one that might be overloaded on a per class basis. In terms of how overload resolution, so as I mentioned, operator new is overloaded. So this means that you can provide a number of different operator new functions, and then which one gets chosen is done based on overloading. So when the new expression is trying to invoke operator new, what it does is it constructs the arguments that are passed to operator new in the following way. The first argument is always the size, the number of bytes that need to be allocated, which has type size t. Then if we have a type which has extended alignment, which probably is less likely to be the case statistically, so usually this isn't the case, but if it is, then there's an extra argument that's passed which has the type align val t, which is basically just the size, or the alignment, sorry, that the object should have. And then any placement arguments are then appended to the list of arguments at this point. So this is maybe better illustrated by way of an example. So if you have an expression that looks like new t, where t is some type, then what this is going to get translated into, in terms of when the new expression invokes operator new, it's going to invoke operator new in one of the two following ways. If the type t has an extended alignment, then what it's going to do is it's going to go for the second option here. It's going to, the first argument is always a size. So since we're trying to allocate storage for something of type t, the number of bytes we need is size of t. So this is what the size is. But in the case that the alignment is extended alignment, we also have to specify what the alignment is. So this is what the second parameter does. In the case that the type doesn't have extended alignment, which is probably the more common case in practice, we're going to invoke operator new just with a single argument, which is the size, the number of bytes that we need for that type T. In this second example here, I have a case where there's placement arguments being used. So placement arguments, in terms of the syntax, they're in parentheses and they come after the keyword new, but before the name of the type that you're actually trying to create. So we have two placement arguments, 42 and F. So again, it's very simple in terms of how the argument list is constructed for operator new to do overloading. We just take the first parameter, again, is always the size of the object that's being created. So we have size of T, and then we just append onto the end the placement argument. So 42 and F just gets stuck onto the end here. And again, if we had extended alignment, we would have this extra parameter for the second introduced in as the second argument here, which is this alignment. And then we just append on to the end of that, again, 42 and F, the two placement arguments. For the purpose of what we do in this course, we're not going to use extended alignment for anything. So the cases that don't apply, or the cases where extended alignment doesn't apply, are the cases that we'll be hitting in this course. And we have a similar sort of thing for array new expression. So here we're trying to allocate an array of 7 objects of type T, where T is just some arbitrary type. This is going to get translated into one of two function calls, depending again on whether the type T has extended alignment or not. But the more common case in this course, the only case that's going to arise is the non-extended alignment case. So maybe I'll just focus on that on this particular slide. So this is going to invoke the first of these two functions. So there's just a single argument to the function, which is just the number of bytes that's needed. So if you're allocating space for an array of 7 objects of type T, how much storage do you need? Well, obviously you need at least 7 times size of T, right? Because that's literally the number of bytes that you need to hold the actual array itself. But the thing you might not think of at first is that there's going to be possibly some additional storage as well, for the reasons that I talked about on that hand-drawn diagram a little bit earlier, which is that when you allocate arrays, the implementation typically will also set aside a little bit of memory. In other words, it allocates a little bit more than what's needed so that it has somewhere to store the size of the array, which can then be used at delete time. So typically there's some small amount of storage which is added on to the 7 times size of T in this case. This extra storage, by the way, is only needed. The storage which records the number of elements in the array so that you can later know how many there are at the time you delete it. This is only really required in the case that you actually need to invoke destructors. Like, for example, if you have an array of int, like a built-in type, you don't need to store the size of the array when you do an array allocation, because you never need to invoke destructors, so you don't ever need to know how many elements are in the array at the time that you're deleting it. It's really only in the case where you have destructors that need to be invoked. In this case, then you'll actually need to store the size, because in this case, you need to invoke the destructors, and you need to know how many objects there are to invoke the destructors for, so you need to know the size of the array. Anyway, so this is what's meant by the comment x is greater than 0 if T has a non-trivial destructor. Also, we can have placement arguments as well with array new expression. So this is an example of that. So here we have new, and then between the keyword new and the type that we're creating, we have this parenthesized list here, which are the so-called placement arguments. So again, the argument list for operator new is constructed in a similar way as before. We just take, for the first argument is just the number of bytes that we're going to request that be allocated, which is going to be 7 times size of T, plus a little bit of extra storage, possibly to store the size of the array, for example. And then we just append on the placement arguments in the same order that they appear in this list here. A few comments about new expressions and deallocation. At first, this might seem a little bit strange. I mean, why would we be doing deallocation in a new expression? But this is in the failure case. So when we're evaluating a new expression, there's the possibility that the allocation function might succeed. In other words, sort of the first step in processing a new expression is we allocate or allocate some memory, for example, to hold the object that we're going to construct. But suppose that the allocation succeeds, but then the constructor fails. It throws an exception. In this case, we need to free the memory that was allocated by the allocation function. So this is done by a deallocation function. And in the case of Well, basically what we have is an operator in language called operator delete, and then there's operator delete square brackets. Sometimes this is called single object operator delete, and then this is sometimes called array operator delete. And the first is used to delete single objects, the second is used to delete arrays. And whether or not we use the colon in front of the keyword new in our new expression, this will dictate how these functions are looked up, because operator delete, just like operator new, can be overloaded, so it can be specified globally and then on a per class basis. And this colon operator controls which of them will be chosen in the case that both the global and a per class definition of the deallocation function is available. Then we have delete expressions and deallocation. So this kind of overlaps with what I just said before. It's just that in this particular context, we're talking about a delete expression rather than a new expression. But obviously, delete expressions need to do deallocation. This is even much more obvious in the case of new expressions. And it's done using exactly the same mechanism. You're using operator delete, the single object version, and operator delete with the square brackets, the array version. So let's talk a little bit about single object operator new. So what I want to talk about next are basically in more detail looking at operator new and operator delete. And again, don't confuse operator new with a new expression. A new expression and operator new are different things. A new expression is sort of implemented partially in terms of operator new. A new expression will cause operator new to be invoked, but they're not the same thing. Operator new basically just allocates memory or somehow knows there's some memory available and returns a pointer to it. But it doesn't construct anything. It doesn't do the object construction and so on. Anyway, so first I want to talk about single object operator new. It's most frequently invoked indirectly. So unless you're doing more advanced programming, typically you don't directly invoke operator new. Usually you'll just use new expressions, and then those new expressions will indirectly be invoking operator new. Operator new may or may not allocate memory. So although it's often referred to as an allocation function, maybe to be more precise, it's really sort of like the function is answering the question, where should I place something in memory? Maybe the answer came from the fact that it allocated some memory and said, well, let's put it in the place that I just allocated memory. But it doesn't, strictly speaking, have to allocate memory. It could, by some other means, know that there's some memory that's available that it could use, and then it just returns a pointer to it. So operator new doesn't necessarily have to allocate memory, although the more common case is that it will allocate memory and then return a pointer to it. It can be overloaded either as a global function or as a member function. So in other words, there's a global version of operator new, but you can also provide on a per class basis. Each class can specify its own operator new if it wants to and overload it. The return type of operator new is a void star. So it's like a pointer to, we're not saying what it's a pointer to. Pointer to some type that essentially the type has been sort of erased. It's a generic pointer. And the return value corresponds to the place in memory where the new object that's being created should be placed. And the first parameter to operator new is always of type size t, and it specifies the number of bytes of storage that's needed for the new object that's being created. Because obviously, if you're allocating space for something, you need to know how big that something is. There are several overloads of the global operator new that are provided by the language and standard library, and I'll talk about these in a moment. And helpful for the purpose of talking about these overloads a little bit later, there's a variable in the standard library called std no-throw, and this is a dummy variable that has the type no-throw t, and the only purpose for this type really is just to force certain overloads of functions to be called. And you'll see what I mean by this momentarily when we talk about the various overloads of operator new and go through some examples. But it's not really meant to be used for any other purpose other than this. So there are actually 5 overloads of, that are provided by the standard library for single object operator new, at least 5 that are listed here. So all of these overloads of operator new, well, first of all of them have void stars, their return type. They return a generic pointer, essentially, a pointer to the chunk of memory where the new object that's being created should be placed. And all of them take for their first parameter the size of this chunk of storage that needs to be allocated. The only difference between them is that they have different subsequent arguments. Either they have none or they have other arguments. This one doesn't have any additional arguments. This one has an align val t argument, for example. This one has a no throw t argument, and so on. So different ones will get picked by overloading depending on which arguments are used in their types when you invoke operator new through a new expression. So the first two overloads that are listed here, they both have for their first parameter size, and basically what they do is they allocate a chunk of memory of size bytes. If that fails for some reason, then they throw an exception of type bad alloc. So these functions will never return a null pointer or something like that. If they fail, they just throw an exit by way of exception. And then we have two additional overloads at the bottom of the slide. The only difference is essentially they take this additional no throw t parameter, and the actual value that's passed into this function by reference, we never actually really ever need to look at it. The only reason that this thing exists is just so that overloading will cause this function to get called. So tag is never actually used anywhere. It's just used for the purposes of overloading. And these bottom two functions, the only difference they have with respect to the top two functions, they're very similar, except in the case of failure, these functions return null pointers. So in the case that the memory allocation fails, instead of throwing an exception and exiting by way of exception, the pointer that's returned by this function or by this function down here is going to be a null pointer. So depending on what you're doing, when you're invoking operator new, maybe in some cases you want to make sure that if things go wrong and you can't allocate memory, that instead of throwing an exception, you just return a null pointer. So eventually the new expression will just return a null pointer. You can do this if you like. But sort of the default behavior, unless you go out of your way to make it not be this way, is that an exception would be thrown if you run out of memory, particularly a bad alloc exception. And then the last overload that we have here is one that in practice you would probably never call directly because it doesn't do anything useful, but it's useful from the point of view of new expressions invoking this operator new overload. So this one takes two arguments. Size, again, is the first argument for all of them. The second argument that it takes, or second parameter, is a generic pointer. And essentially what this overload does is it just returns this pointer back. And this might seem kind of useless, but it turns out to be very useful for the purposes of creating objects in places in memory where you already have memory allocated, and you're trying to use a new expression, and that you want to have the new expression create an object at a particular place in memory without actually allocating memory. And this is what purpose this particular overload serves, and we'll see this in more detail when we go through some code examples later. And then we have a few examples of using single object operator new. So the first example we have here, let's see, we're using operator new to allocate. Remember, the first argument that's passed is the number of bytes to allocate. So if we want to allocate enough storage for a string, then obviously we need size of string bytes. So this is going to cause operator new to allocate enough bytes to hold a string object. And then we take the return value of this, of operator new, and we cast it to a pointer to a string, because remember the return type of operator new is void star. So it's like a generic pointer. It points to something, but we're not really sure what it points to, like what type. Which sort of makes sense here, because when operator new returns this pointer, there's actually no object sitting in the memory. It's just raw bytes until we actually construct something there. But because you can't convert from void star to string star without an explicit cast, we have to include this static cast here for that purpose. And because the particular overload that's going to get picked, in this case, we're basically invoking operator new with a single argument, which is a size t. So if I back up to the previous slides here, the only function that could be called here would be this first one, or I guess potentially the second one if you had something with extended alignment. But in this case, we don't have extended alignment. So it would just be this first overload that would get invoked, which is going to have the behavior of either returning a pointer to the memory that was successfully allocated, or it throws a bad alloc exception. So if I go back to the code here, we can safely put this assertion in here and be confident that it will never fail, because if this memory allocation fails at this in operator new will not exit normally. It will throw an exception. So if it throws an exception, we'll never hit the assertion, in which case we could never observe a pointer that wasn't properly initialized to something other than null. In the second example that I have here, we're using a place, or we're using an additional parameter to operator new, this stood no throw, this variable which is defined in the standard library, which has the magical type that we saw earlier, which was this type here, no throw t. So when this, through overloading, what this is going to invoke here, it's going to invoke the version of operator new that takes a size t and this no throw t type, which would be, I guess, this one here. So this particular function has the behavior that if the memory allocation fails, it returns a null pointer. So, and it never throws any exception. So basically, you're always going to exit normally from this function, and either it returns a null pointer or a non-null pointer, depending on whether things succeeded or failed. So if I go back to the code example here, in this case, I couldn't put an assertion here saying, like on this line here, line 18, I couldn't say assert SP. Because SP could be null when I hit line 18, because if this memory allocation fails, this will return a null pointer, SP will be null. And then the last example I have here is an example where I'm using the very last overload that was introduced, basically this one here on the previous slide. In this particular case, we're providing the size. This is basically corresponding to the size t parameter, the number of bytes that we need to allocate. And then we're passing a void star pointer. So this is going to, in terms of the overloads, the only function that's going to match, none of these will match. It's going to be this function here, which will match. And this basically just returns back whatever we pass in for this parameter here is just going to get returned back to us, and it doesn't do anything else. So here, the thing that we're actually passing into it is the address of I. So what it's going to do is it's just going to return back the address of I and assign this to IP. So this is just a very convoluted way of writing something like I star int star IP equals the address of I. You would never write code like this normally. This is just kind of illustrating the various different overloads of the single object operator new. But this, if you were directly invoking operator new, it would be useless to ever use this overload because it doesn't do anything. At least these other two overloads, they actually do something useful. They allocate memory. So if you're directly invoking operator new, you would probably never directly invoke this overload here. It's not really very useful.